Hello everybody, this is Dr. Pennington again, and I would like to talk to you in this video about the concept of atomic and ionic size. So let's talk about atomic size first. We'll get on to ionic size later on. Now, of course, when we talk about atomic size, we're talking about sizes of atoms. Ionic size, we're talking about sizes of ions, and that can be anions, cations, or in some cases, both. Alright, so let's talk about atomic size first. There are several trends that you will have seen about things that vary across the periodic table, and one of those is, for example, the atomic number. Increases left to right, increases left to right across a period, and increases top to bottom down a group. Alright. There is one particular misconception that goes along with that, and that is to do with atomic size. As the atomic number increases, the assumption is that the atomic size increases. In other words, in period 2, lithium is the smallest atom, neon is the largest atom. Alright. In period 3, sodium is the smallest atom, argon is the largest atom. Alright. Now, it turns out that that's not the case. It's more complex than that. And the rationale behind it is to do with electron configurations that you've seen before. Alright. Let me show you a picture. It's kind of a 3D picture of relative atomic sizes. And notice what you think you see when we look across, for example, in period 2, starting here. Lithium, beryllium, boron down to neon. These numbers here are the actual radius, alright, shown in picometers. And when we look at lithium, 152 picometers in size. That's the size of one lithium atom. What we thought was the case was that neon would be the biggest. In fact, neon would be the largest out of all these period 2 elements. And of course it's not. It's actually the smallest, more or less. Sodium in period 3, biggest. Argon, oh, what do you know, it's the smallest. It's kind of exactly opposite the way we thought it was. So we have to do some thinking about what is it that's making going left to right across a period, what is it that's making the atoms actually get smaller. Now going down a group, the trend that we thought was true actually is true, and this kind of makes sense. Alright, as your value of n increases, your orbitals get more diffuse and the electrons get further apart, and so your atoms get bigger, and that's essentially the case. So as the atomic size, as the number of protons increases around the nucleus, the number of protons in the nucleus increases, the number of electrons around it increases. As the value of n increases, then that means you have a bigger atom. That's why all the elements on the bottom row here are all the biggest, as you would expect. But this leads to a particular question. Why, for example, why is boron bigger than nitrogen? Shouldn't it be the other way around? Okay, well, based on what we were looking at here, well, I don't know, maybe it should be the other way around, but of course it's not. Let's see if we can figure it out. Alright, let's look at the electron configurations of both of these atoms and we'll see the pattern. And we'll actually see the pattern that is reproduced in periods 3, 4, and 5. The pattern's actually very simple. Let's look at the electron configuration of boron. Alright. So boron has 5 protons and thus 5 electrons. So when we think about the electron configuration of boron, 1s1, 1s2, 2s2, 2p1. That's the electron configuration of boron. Alright. 1s2, 2s2, 2p1. That's boron. Now when we look at nitrogen, nitrogen only has 2 extra electrons. Alright. And if we just go back here, we know nitrogen is here. 1s2, 2s2, 2p1, 2p2, 2p3. So we end right there. We end in our p block, halfway through our p block. So therefore, 1s2, 2s2, 2p3. All right. One of the things that's important here is the orbitals that the outermost electrons are in. All right, and those are the p orbitals. Now the fact is, a 2p orbital, no matter what element it's in, has the same energy. A 2p orbital containing the electron from boron has the same energy as 2p orbitals containing the 3 electrons from nitrogen. Meaning, these p orbitals are equally distant from the boron nucleus as they are from the nitrogen nucleus. All right, essentially. But we have to, and so that means that the electrons are, in theory, the same distance from the nucleus in each case. Now, if that was the case, then these two would be exactly the same, because the p orbitals are equidistant from the nucleus, which means there has to be something else going on. And there is something else going on. It's something to do with effective nuclear charge. Has the symbol ZF. Z for charge, EF, F for effective. What is the charge felt on the electrons by the nucleus? If you remember, the nucleus is positively charged, it's full of protons. All right. Now for boron, how many protons are inside the boron nucleus? Well, it's the same as number of electrons, it's plus 5. So I'm going to say inside that boron nucleus we have 5 protons. Inside the nitrogen nucleus we have 7 protons. All right. So that means in nitrogen we have a higher charge pulling on those outer electrons than we do on boron. Which means the effective nuclear charge felt by the electrons in nitrogen is higher than it is in boron. In other words, the effective nuclear charge for the outermost electrons in nitrogen is bigger than what it is for those outermost electrons in boron. And because that charge felt by those electrons is higher in nitrogen, that means they are pulled more closely towards the nucleus. It's kind of like you have a stronger magnet inside the nitrogen than you do in the boron. And because those outer electrons are held more tightly, they are actually held closer. All right? And so that is why, as you go across the p group here, from 1, 2, 3, at least from 1, 2, and 3, and then 4, 5, and 6, you see a relative overall decrease in size. Because all these outer electrons, 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6, they're all in the same energy level, they're all in the same orbital, they're all equidistant from the nucleus, but in each case, the charge on that nucleus is increasing by 1 unit. Therefore, the effective nuclear charge is increasing each time. So if I was to ask you out of boron, carbon, nitrogen, oxygen, fluorine, and neon, in which case did the outermost electrons, the 2p electrons, experience the highest effective nuclear charge? Well, that would be neon. And that is why those outermost electrons in neon are held most tightly, and hence why neon is smallest out of those groups. Notice the same trend is seen for the 3p orbitals, the 4p, and the 5p. It's exactly the same trend. All right. So hopefully that makes a little bit of sense about relative atomic size going down a group and across a period. Now let's talk about ionic size, because this can be more complex, but it's really not. It really isn't that much more complex. There are a couple of rules that we want to make sure we have an understanding of before we go any further. And that is, let's go back here again. Remember the species that lose electrons and then the species that gain electrons? The species that lose electrons are essentially the metals that we can say, we have over here, more or less. And then the species that gain electrons are the non-metals over here. All right? Now, if we think about, for example, in particular, the group 1 metals, all right? If we look at, say, sodium, all right? Sodium has 11 electrons. So if we just do this, 1s2, 2s2, 2p6, 3s1. That's the electron configuration for sodium. The outermost electron is in the 3s orbital. When we remove the electron from sodium, as we know sodium very easily does in a very exothermic fashion when it donates it to water, for example, what we get left with is this. Notice there's no electrons in the 3s orbital anymore. Therefore, the highest orbital where electrons are occupied becomes considerably lower in energy and smaller in size. So what that means is the sodium actually shrinks when it loses the electron. And that is the case for most atoms, most metal ions that lose electrons. Alright? Notice the size of the relative size of the lithium atom. And then when it loses the electron, it shrinks. That's the original size of the atom, that's the size of the ion. Alright, because in each case you're losing electrons from the outermost shell, your atom shrinks. Alright? It doesn't shrink quite as much when you're talking about groups 2 and 3, but it's still exactly the same concept. Alright? So any atom that loses electrons when it forms an ion or forms a cation will shrink when it loses electrons. It's always the way. You'll never see a situation where something gains electrons and gets smaller. Now anions, on the other hand, the main group elements, we said, for example, chlorine in group 7, it wants to gain 1 electron to become happy. Oxygen wants to gain 2 to become happy. Phosphorus wants to gain 3, and so on. If when you lose electrons you get smaller, it would make sense to assume that then when you gain electrons you get bigger. And that is absolutely true. And so when we look at oxygen, for example, neutral oxygen. Oxygen, after gaining 2 electrons, it's increased in size because of the extra electrons. Bromine. Bromine atom. Bromine ion, it gains an electron, so it gets bigger. So the general trend is a species that loses electrons to form an ion gets smaller. A species that gains electrons to form an ion gets bigger. And that is the general trend that you can always say. Alright? So, let's see if we can answer a couple of questions here. Choose the larger species from each pair. I should say or set, because part D asks us about 3 atoms, 3 species. Gallium or bromine? Now we need a periodic table here to help us figure this out. Where is gallium? Hang on a minute, let me delete all this bollocks that I put on here. Gallium is here. Bromine is here. These are in the same period. So what did we say before? We said the atomic size decreases left to right. So therefore the smaller one we'd expect to be bromine. Alright? So therefore the larger atom would be gallium. And that's absolutely true. Magnesium or magnesium 2+. Well, magnesium is here in group 2. What does magnesium do? Does it gain or lose electrons to form an ion? Well, it's a metal. It loses, in this case, it loses 2 electrons. It's in group 2. So therefore, when it loses those electrons, it shrinks. Kind of like the, well, no, I won't say that. A metal that loses electrons gets smaller after it's lost those electrons. So therefore, the larger species is the original magnesium. All right. Now, chlorine, Cl-. Same species, but in this case we have gained electrons. Now chlorine is over here. That's the size of chlorine. Alright. So when chlorine gains an electron, granted it doesn't become argon because it still only has 17 protons in its nucleus. And because of that, anytime you gain electrons and retain the number of protons you had before, you get bigger. So therefore, chlorine gets bigger, where if we're asked to choose the larger species. Now, this last one, this is a little bit more complex. Choose the larger species. In this case, it should say largest. Calcium 2+, argon, or chloride. And the question says these are isoelectronic. Now, what do you think iso means? Well, iso as a prefix means same, as in isomer, or isotope. Isotopes have the same number of neutrons but different numbers of protons. Isoelectronic, what do you think that means? Well, it means same number of electrons. All right, let's see if we can figure it out. Calcium 2+, all right, where is calcium? Calcium is here. Originally, calcium had 20 electrons. If it's lost 2, then calcium 2+ has 18 electrons, all right? And we're going to figure out the number of electrons for argon and for chloride. All right, let's do argon first. Argon, neutral argon, has 18 electrons. Chloride, after it gains 1 electron, also has 18 electrons, because originally it had 17. So they all have 18 electrons, which would suggest, well, aren't they all the same size? They have the same number of electrons. Well, that would be true if their numbers of protons were the same. And as you would imagine, they are not the same. Some of you might have guessed that already. How many protons are there in calcium? Well, the number of protons is the same as the atomic number. Calcium had 20 protons, so calcium 2+ contains 20 protons. In other words, 20 protons. So inside that nucleus there's a charge of 20+, or plus 20. Argon has 18 protons, and so inside its atom, inside its nucleus, it's got a charge of 18+, essentially. And then chlorine, it gained 1 electron to get 18, it originally had 17. So therefore, 17 protons inside its nucleus. 17+. So the question then becomes, I'm not concerned about these electrons because these are all the same. These are nothing to do with where my answer comes from. It's got to be these 3 numbers. If I have equal numbers of electrons around my nucleus, what do these 3 different numbers tell me about how closely those electrons lie towards the nucleus? In which case do you think the electrons are pulled the closest? Well, it's the case where there's the largest positive charge. All right. Which of these 3 has the highest effective nuclear charge? Well, it would be the calcium 2+, because it's got the highest number of protons. Which of these would have the lowest effective nuclear charge? Well, that would be the chloride, because it's got the smallest number of protons. All right. Highest effective nuclear charge, lowest effective nuclear charge. Therefore, the one with the lowest effective nuclear charge means that those electrons are held the least strongly. Therefore, the larger species. Therefore, the larger species is chloride. The smaller species is calcium, 2+, and in the middle is the argon. Now, the question didn't ask us to do this, but we could say the chloride is bigger than argon, which is bigger than calcium 2+. All right? And so that is how you distinguish and figure out effective nuclear charge and atomic and ionic size. All right, thank you.